Okay, so last time we left off with talking about, well, we're going to solve the Schrodinger equation. And remember, we derived the Schrodinger equation just using pure thought, and it has this form that a state evolves according to what we called a Hamiltonian, and we just derived it as just some Hermitian operator. But it's the Hamiltonian, it's the energy operator. It's the thing that measures the energy. So, kinetic plus potential. And last thing I did in class was basically show you in a little bit of a hand-wavy way why it might be the energy by using the so-called correspondence principle and arguing that, well, time evolution in quantum mechanics should at least give you the right thing in classical mechanics in the right limit. So if you have some classical variable QC, it should correspond to the expectation value with respect to your state of the corresponding observable. So the time evolution of the classical guy should correspond to the time evolution of this expectation value. That's the correspondence principle, and from that we derived that, that H should be the energy operator. It's a bit hand-wavy. I'm not even sure it's, it works in all cases, this kind of correspondence. But that's all I'm going to say about it. There's, I think, other ways of showing it's the energy operator, but we're just going to go with it for now. This is the thing that we're going to be looking at solving. And the first thing to solve, of course, is a free particle. It's just the particle hanging out on a line and moving around with some momentum. So the energy there is just p squared over 2m, just the kinetic energy. And that's what we're going to look at. And in particular, we want to know what the wave function is associated with, a state psi of t, right? What's this wave function? Well, we know we can stick in a completeness relation in the p variable. Why? Because, see, this has a p operator in it. This is like big capital P. This is a momentum operator. So if you see that, right, is in your Hamiltonian, it is just depends on P, then you should think right away, well, we should use the, quote unquote eigenstates of the P operator, which are the little P kets, which are pseudo eigenvectors and, all the things we learned about them from last time. So if we want to calculate this, we probably don't want to deal with X in particular. We want to deal with P. So automatically here we have our little completeness relation. And, instead of psi of t, we just put in now the solution to this equation. And you derived it on your homework. And we talked about it when we talked about in a stationary states. If h doesn't depend on time, which it doesn't here, it's just p squared over 2m, then we can just exponentiate it right away, and you get it over h bar, h acting on psi 0, the initial state. And you see it's quite easy now. H is a Hermitian operator. We can take its dagger and we can act with it on the left if we wanted. And of course that comes at the price of putting in a little plus here instead of the minus I. So we can calculate this out. We know what this is from last time, right? This is the wave function associated with a particle with a fixed momentum. So it's e to the I px over h bar divided by square root of 2 pi h bar. And now we're acting with the evolution operator here on the P bra. Much more convenient because, you know, we know how this works. P is an eigenstate of H, right? Because H just depends on P. So you just pop out the eigenvalue here. And so you have, let me write out the exponential here is exp. You have IPX over H bar, and then you just have minus IT over H bar times the energy now evaluated at that momentum P. That's just, you know, this is just P squared over 2m, little p. Because, you know, the eigenvalue just pops out of there. And here you have, for the rest of it, you have P psi naught, the initial state, divided by this normalization, square root of 2 pi H bar. And what happens here is this, right? This is just the momentum space representation of the initial state, your initial wave function. So it's just, you get psi tilde of P. So you see, all of the evolution in time is kind of in here, right? Here's the T. This is the only place where the T appears. So it makes things kind of nice because then this is all just stuff having to do with the initial wave function, the initial state. And then this is what evolves it in time, this part in particular. This is the time evolution. So it's sort of like solving it exactly for any arbitrary sort of initial condition. And it's convenient to change variables. There's a lot of H bars running around. So what we typically do is we define K. This is the wave vector, which is P over H bar. It's so that you don't have this P over H bar running around. And then you'd also define an angular frequency omega of K, which is just the energy divided by H bar. Again, to get rid of this H bar, right? And, you know, this you can write as H bar squared K squared over 2m H bar, so that one of the H bars cancels. So it's H bar K squared over 2m. And then you also, to get rid of these factors and to sort of make this a little bit better, so that you can use a function of K instead of P. We define an amplitude A of K, which is square root of H bar times psi tilde, the Fourier transform. And maybe we should put a little 0 here to indicate that it's the Fourier transform of the initial state, of the initial wave function that you start with. And it's a function of P, so it's a function of H bar K. And so if you change variables here from P to K, then the end result here for the time-dependent wave function, I'm just going to write it down, just a little bit of algebra. These things, this change of variables just cancels out all the H bars, and you get 1 over square root of 2 pi, then the integral from minus infinity to infinity of now dk. You can sort of see, if you like multiply by square root of H bar up here and square root of H bar over here, then this just becomes H bar, so you get dp over H bar, which is just dk. right? dk is dp over h bar. So you get a square root of h bar in the numerator, and that's what you call the amplitude, this ak. So it's all just a little bit of algebra, but it's this amplitude. And then it's what? E to the I kx minus I omega as a function of k now, t. And that's what it is. That's the solution to the free particle. And what we can think about what, you know, what this is, this amplitude comes from the initial state, and it gives you the envelope, right, for your wave function in momentum space. And it's just the Fourier transform of your initial wave function. And so your initial wave function, what is it? Well, we're thinking about a particle, right? That's kind of hanging out at some position x, right? So your initial wave function is going to be localized at some position, x naught, say, and it's going to have some momentum, right? P. It's a little particle living on a line, and so the initial wave function is going to be some wiggly thing that's kind of confined inside an envelope that describes the uncertainty in the position. And the little wiggles tell you about the p, because that's the e to the ipx part. And of course, you know, the wave function is a complex function, so you can imagine I'm plotting the real part or something. It's like the real part of, you know, psi of x at t equals 0. And so what should happen is this time evolution, what should it do? Just intuitively, right? It should move this wave packet, right, along, and should continue wiggling, but it should just move over with some velocity, right, related to the initial momentum. It should, you know, should be the momentum divided by m. And in recitation, I showed you that if you have a Gaussian, for instance, for the wave packet with some spread here, delta x, if you look at the same function, if you Fourier transform it, the initial state, which is going to be our a of k, you know, modulo some factor of h bar, then as a function of k, you'll get another wave packet like this. And what I kind of showed in recitation, and what's, you know, we know from the uncertainty principle, is that it'll have, you know, its own width, delta k, now in k space, same as momentum space, you know, up to a factor of h bar. And we know the Heisenberg uncertainty principle tells us that the spreads are inversely related to each other. And this is basically what I showed in recitation, is how the Fourier transform naturally gives you this inverse relationship between the wave packet in Fourier space and the wave packet in, you know, position space. So, and that's kind of how it goes. And we can study now this in more detail. That's what we're going to do now, is look at how it actually evolves in time. Any questions, though, about that? Or what we did? We just immediately see, using this operator language, we can solve the free particle Schrodinger equation just immediately. Real easy. Maybe this is a good time to do a little demo here of what this looks like, right? So you can actually use Mathematica to solve the Schrodinger equation if you want. It's a little bit tricky, but, you know, it's not so bad. So you can set up an initial wave function. This is the thing that we're talking about, the Fourier transform of which is, you know, this amplitude a of k. And here I set it up to be a Gaussian centered at minus 20 here in the x direction. So a little Gaussian with the little wiggles representing, again, so this is like the real part of the wave function. The little wiggle, the real part is blue. The orange is the absolute value of the wave function, which gives you the envelope, right? That's the real and imaginary part, you know, the magnitude of the complex function here. And so you have this time evolution, right? This is just a Schrodinger equation. This is minus two derivatives. I set h bar equal to 1. So it's 1 over 2m, m is equal to 1. It's minus two derivatives acting on the wave function here. And this is the initial condition, and you can evolve it and see what happens. So at time t equals 0, you have this nice Gaussian. And as you sort of move along in time, it'll shift, right? It'll move along. And you'll see that the uncertainty in the position kind of widens a little bit. But overall, it just kind of moves along, right? With that initial momentum. And where's the initial momentum? It's right here. It's this e to the ikx. It's this k here, kb, which I set to 1.5, that gives you the initial momentum. And that gives you the wiggles. So the more it wiggles, the faster it goes, right? And then the envelope tells you about the uncertainty in the position. And of course, you can probably, maybe next time, or maybe in a recitation or something, we can take the Fourier transform of this and see what that looks like, what this looks like in Fourier space instead of position space. So position space is a natural thing to think about because we're thinking about a particle. It's localized at, you know, minus 20 with some uncertainty, and then it gets, you know, has some initial momentum and it moves off with that momentum. Okay, so that's what happens, and you can just see that just by actually solving the Schrodinger equation. But let's think about this amplitude AFK in more detail. It's of course going to have some magnitude and a phase, which you call it either I 5K. It's a complex function, so I can always break it down into you know, a magnitude and a phase. And so if we think about, sorry, my light's if we think about this integration here, then what's this integration? What's the integrand in here? Well, it's the magnitude here of a of k, right? And I can combine everything else in the exponential. It's e to the I kx plus 5k minus omega k t. And now we're going to you know, try to analyze this. So let's think about it. We're integrating over all k. Okay. This is just some smoothly varying envelope thing like this red. You know, it's some Gaussian bump thing. It's the amplitude of it's the magnitude of the initial wave function. There's going to be some bump. But this is a very rapidly oscillating function, right? This is oscillating like crazy. It's the little wiggles. And if you're integrating your crazy oscillating thing, then, you know, for the most part, if you think about it, you know, you're integrating some crazy oscillating thing, it's going to cancel out, right? The integral of a crazy oscillating thing is 0. If it's oscillating like crazy, you know, the different, it's going to be as much positive and negative. If it's like a sine wave or something, and it's oscillating like crazy, you know. So for the most part, the integral will be 0 when we're integrating up this dk, and it'll only have contributions when this part is kind of slowly varying, right? So there's something called the stationary phase approximation, which you might or might not see in math methods, I don't know. Who has seen the stationary phase approximation? I highly doubt it, but it's possible. Has anyone seen the stationary phase approximation? Or heard of it?
No, I've heard of it, but your review would be nice.
I don't believe I've heard of it
See
ever.
what you write down, and then I'll tell you if I've seen it or not.
Well, if you haven't seen it in the context of this kind of integral with an e to the I, then I doubt you've seen it.
I have seen that. I have
Oh,
seen
okay.
papers. The earlier expression of the oscillation that you've written.
Yeah.
Yeah.
Okay. Well, in any case, we're going to go through it. So if this is oscillating like crazy, then the only contribution to this integral is where this is slowly varying. So slowly varying means that if you think about this thing up here, you want a place where this has some, as a function of k, it's got this thing, I don't know what to call it. Let's call it, let's call it big theta or something, theta of k. So this varies somehow in k, and so you want to find the places where it doesn't vary very much, where it's kind of flat, where it doesn't depend on k very much. And those are the critical points, right? It's where theta has like a local minimum or maximum, right? This is the places where the curve is kind of flat, right? The critical points. And at those critical points, d theta dk is 0. It's where you have a little local maximum or minimum in this exponent. And at those maxima or minima here, maybe I'll make theta blue or something. At those maxima or minima, theta is not changing very much. You kind of, as you roll around the minimum or maximum, it's just flat, right? So that's the stationary phase approximation. You just look for places where this exponent thing is slowly varying, and that's where the derivative of it vanishes with respect to the integration variable k. So you look for places where this is true. And if we work that out, it's d dk of kx plus 5k minus omega kt, right? And what is this? Well, k acting on kx just gives us an x. Then we get a plus d phi dk, which is sort of a derivative of the phase of this guy, the initial amplitude. And then we have a minus t d omega dk. D omega dk, we know what it is. D omega dk is just d dk of h bar k squared over 2m. So it's h bar k over m. And if you remember, that's the momentum, p divided by m, right? Because h bar k is the momentum. And what is this? Well, this is just the velocity of the thing. The initial, it's just the velocity. The sort of the number, the classical one, the p over m value. And so what does it mean if all of this is equal to 0? Look, this is nice. It tells you that the contribution to this integral happens when x is equal to, if we put it all over to one side, we get when x is equal to v, and I'll put a little g here for group velocity because it's really like the velocity of the whole wave packet that this thing is, that this thing gives you, this p over m. So it tells you how fast the whole thing moves, the whole wave. So I'm just going to call P over mvg, and then so from here you see that x has to be equal to t times vg minus d phi dk. This thing does not depend on time, right? Because it just comes from the initial wave function, the initial Gaussian bump thing. So this I can rewrite as vg t minus some tau, some time, which you know, tau is just 1 over this vg of d phi dk. And so yeah, so it's and this, of course, you find the critical points. So this is at a particular, you know, k bar. So this is all evaluated at some k equals k bar, for which you're at that stationary point. Okay, so this tells you basically that, well, so now we're going to actually do this integration, just keeping in mind that the places when we integrate over k that contribute the most are ones where this phase thing vanishes, and that's the stationary phase approximation. And this happens at a particular k bar, somewhere along this integration. Which k bar? The one that, you know, makes this equal to 0. And when this is equal to 0, then we know that x has to be equal to this, you know, as long as we're evaluating at that particular k bar. And k bar will be, of course, you know, related to this initial momentum that you put in to the wave packet. But it says what happens is that x just kind of travels along with this velocity vg. And vg is this guy. Vg here is h bar, k bar, because that's at the critical point over m. So let's see a little more. So far as in principle, we can find such a k bar where this is 0. And now we can stick this back into here. And what happens there? So what you want to do is you want to expand the exponential around that k bar. So what you do is you expand theta of k around the stationary value k bar. And what do you get? Well, you get let's see. So you want to expand, for instance, this guy around k bar and this guy around k bar, because those are going to be the major contributions to the integration. So what we get in the exponent is, well, we get the kx. That's a linear term. We can leave that. We can actually, we can leave the phase because that'll come out. And then we expand the omega. So we'll expand the omega piece. And how we do that is we just do the Taylor series, omega k bar. That's the 0th order term, plus k minus k bar, d omega dk, right? Evaluated at k equals k bar. And then we can do a higher order term, the 2nd order Taylor series term, which is k minus k bar squared over 2 d squared omega dk squared evaluated at k equals k bar. And so on. And all of this is times t. And when we substitute back into the wave function, what we find is that psi of xt is now 1 over square root of 2 pi integral dk here. You got the amplitude. This we can now evaluate at k bar. If it's slowly varying, it's okay if we just evaluate it at k bar, so you can do that. And here you have e to the I kx plus phi of k, this phase, which these are we're leaving alone for now. And now we're going to put in this expanded out stuff. So the first term is minus omega k bar t. Next term is this guy is minus k bar. What's d omega dk? D omega dk is vg. So it's this velocity times time. That's from here, right? D omega dk evaluated, you know, at k equals k bar. So I should probably put bars here. Yeah, just this vg. So that's this term. We're going to drop this one because that's higher order. We're just going to keep everything up to linear terms in this k variable. So there you go. That's what the new exponent is. And now this integral is a little bit more manageable because now there's just a k here and there's a k there. And what else? Well, there's this phase, phi of k, right? That's okay. Actually, we don't have to keep we can keep this k too. Basically, we know, right, that the original wave function, right? What do we know? We know about this a, right? The original a. If we go back here, we know this guy. This we sort of know what it is. It's just the Fourier transform of the initial wave function. And go all the way back to here. AK is just this guy. It's the Fourier transform of the initial wave function. So this guy's okay. So we can sort of keep the a of k around even with the phase. So this is, we know this. It's the initial condition. So let's keep that around. What we're doing here is we're trying to rewrite the integral in a nice way to see what happens to the wave packet. And I know it seems kind of arbitrary not to expand this guy, but it works because we'll know what this stuff is. And all we're doing here is we're trying to get rid of some of this extra k dependence in the omega by expanding omega around k bar, which is the stationary point. So that's yeah.
I just have a quick question. I missed the part where you said you're gonna drop the second order part of the Taylor series expansion.
Yes.
Why'd you say you're dropping it?
Well, okay, so the argument is, right, that in the stationary phase approximation, we're arguing that this integral only gets contributions when k is approximately equal to k bar. And k bar is one of these critical points where the derivative of this exponent vanishes. And I haven't said what the k bar is, but it's some value of k where this integral gets the largest contribution. So then in this exponent, I can expand this exponent around k bar however I want. And I know that I'm not going to mess up the solution very much because I know that's the place where the integral gets the most contribution anyway, the stationary phase approximation. So what I want to do is I want to take this omega, which is a function of k, and I want to expand it around the stationary point. And that's what I'm doing here. I took this part, which I'm leaving alone, and this I'm expanding the omega around k bar, the stationary point. And if the stationary phase approximation is good, then I don't have to expand very far. I can just keep the first two terms, say, the value of omega at k bar, and then the first term in the Taylor series.
Okay.
Around k bar. And I'm saying, well, stationary phase, probably this part won't matter. I'll just not include it.
Okay. Thank you.
Does that make sense?
Yeah, it does.
And this part, I could in principle expand too, but I'm going to leave it alone because I can actually treat it exactly. I know this. I'll be okay with this part, as you'll see.
Okay.
And anyway, it's more exact this way anyway. The point is, again, stationary phase tells you I can expand the whole exponent around k bar, and now I'm just choosing to expand different pieces of it to get the solution in a nice form to see what happens to the wave packet.
Okay. Okay.
Okay, great.
I just
Hopefully
wanted to clarify, but how can we be sure that the second order kind of vanishes? Because typically you drop something only because it vanishes, right? Like it's so close to zero, it doesn't matter.
Yeah, that's right. We'll see. We'll see. We'll get a solution, and then we'll go back and do a self-consistent check, right? We'll see when this term gets big. So
Okay,
we'll
that's
see.
what I was hoping. All right, cool. Thank you.
Yeah. Okay, so we have this, and now we see that you have this k, and there's a k over here. Those are the only k's. So this whole thing is equal to 1 over square root of 2 pi. Integral from minus infinity to infinity, dk, a of k. And now we have e to the I, kx plus this phase, phi of k. And then we have, so actually let me recombine things a little bit. So we can put the e to the I phi of k back with this guy, and this just becomes a of k. And we can put the e to the I k x with this guy minus vgt. And everything else just comes out of the integration because it doesn't depend on k. Everything else, like this part and this k bar over here, it just comes out. So you get e to the minus I omega evaluated at k bar t, and then you get the plus I k bar v sub g t. And this is just an overall phase, right? So it's not physical, as we learned. You know, kets in quantum mechanics are physical only up to an overall phase. So that part doesn't matter. And what this thing is the Fourier, it's the inverse Fourier transform, right? IK inverse Fourier transform of the original wave function, except not evaluated at x, but evaluated at x minus vt. So it's just a shifted. And if I undo the Fourier transform, inverse Fourier, then I just get back out the the original wave function, except not at x, but at x minus vgt, evaluated, at t equals 0. So you take your, this is the original wave function, your initial condition, except it's now your initial condition shifted by vt. So all this is saying is that your wave function in the stationary phase approximation, it doesn't change shape. It stays the initial, it stays shapes just like the initial wave function, except the whole thing just shifts by vt, right? And it moves in the right direction. And yeah, so that's kind of nice. It tells you that if you can drop the second order term, then the evolution of this wave packet is just as if you set it up initially, and then the whole thing just moves. I don't know if you can see me in the Zoom. It just moves with the same shape as when you first set it up at t equals 0. So what do we have here? Now we can ask, when does this thing start to? When does So as Mina was wondering here, when does this thing start to contribute? When is that important? It's important when, this becomes large, right? Obviously. So, and it becomes large when multiplied by t here. And this all lives inside an exponential. So it's when that becomes of order 1, right, that becomes a problem. So it becomes bad if 1/2 k minus k bar squared h bar t over m. This is, if we calculate d omega squared dk squared, that's 2 derivatives of k on h bar k squared over 2m. So that just gives us h bar over m. So that's what the h bar over m is, times t. When this thing is bigger than 1, then you start to get problems. So when will that happen? The maximum value of this must be related to how far in this integration over k do we range outside of the stationary point. And the stationary point is going to be, in k space, just the, it's going to be given essentially by the envelope function of your initial amplitude. The k bar is just going to be the initial value of this peak in k space. And we know that there's going to be some spread associated with it. And so the maximum value of this really is, kind of delta k. It's the spread of your envelope in momentum space. So this becomes a problem when the spread in your envelope function squared h bar t over m is bigger than 1. Or if you want, you see this tells you that it's when t is bigger than a characteristic time. And the characteristic time is, you multiply out, you get 2m divided by h bar delta k squared. And we could convert that to a momentum. The delta k becomes p over h bar, so it's alternatively 2m h bar divided by delta p squared. So it's when the time of your evolution is bigger than 2m h bar divided by the initial uncertainty in the momentum. Or if you want the initial spread of this guy, that's when the approximation breaks down. And you can see that in the little example, right? In this example, basically when you start off with this bump, for a short time, it kind of maintains the same shape, and that's that stationary phase approximation. But eventually, once the time gets large enough compared to this, characteristic time, then you get in trouble, and the wave packet starts spreading out and changing shape. You see it gets wider, and that's exactly when that higher order term, this guy, starts to dominate the solution.
Okay, so I do have a question to interrupt you, but okay, so what you're saying is, in this case, what we want to do is keep the shape the same, right? And avoid.
Well, we don't want to. It's telling us that that's what happens.
Okay, so this is something that, like she had said, that we can't just get rid of this, but you're saying at first it'll keep its same shape, but then after a certain amount of time, then that's when it starts to change shape. That's because this actually is a valid part of it. The higher order terms are, right?
Yeah, that's right. That's right.
And we can find that characteristic time by setting the second order term equal to 1 instead of, right now it's greater than 1, right?
Well, what we're saying, so this is in the exponent, right? It says e to the I theta up here, I theta. When this theta is of order 1, when you have a term that's of order 1 here, then that's like already, that's already starting to oscillate quite a bit. So we're just going to estimate that this term starts to contribute when it's of order 1 or bigger than 1. So that's all we're saying here is that when it's bigger than 1, bad stuff's going to happen because it's going to start contributing in that exponent. And then we still don't know what this k minus k bar is. And I'm arguing that if you have some initial shape for your envelope, then the maximum this can be is just sort of the width of that envelope, right? So that's delta k, and that's related to the uncertainty and the momentum. And so this gives me a kind of bound on what, it gives you a criterion of when that term starts to contribute. And it just gives you this characteristic time. It's just rewriting this inequality. It's bad when this is bigger than 1. It's the same as, t being bigger than this characteristic time.
Oh, okay. Yeah, I see it now.
Yeah, and just rewriting this inequality to get the characteristic time. If you want, I can also write this inequality as, t over tc bigger than 1.
Right.
So yeah, but, these days you can just put these things in Mathematica and sort of see how it works. Mathematica has a hard time because, quantum mechanics is difficult because of all the oscillations in the complex function. So it makes the numerical sort of differential equation solver very unhappy when you have lots of oscillations like that, but it can still do it. At least on my laptop, it's okay. It's a little slow. Okay, great. More questions.
Just out of curiosity,
Sorry?
I just wanted to ask a question, like a general question.
Yes.
This whole concept of wave packet and the whole concept of wave packet, this also applies for photon wave packets, right?
Yes, yeah.
I was just wondering because there is the mass term m. What does that become for massless photon?
So in the photon case, you have a different energy. You can probably just phrase everything in terms of the E and B fields. And so the energy would be like the electromagnetic field squared. So it's whatever the proportionality constant is in front of that. So it's that problem looks different. You would formulate the energy in a different way, right? You would have to put in the electromagnetic energy, and you'd have a different kind of Schrodinger equation. So I don't think there's a direct connection. It's not like, the photons is just the massless version of this. It's not like that. It's you have to bring in the actual forces, right? The energy is involved in electromagnetism.
Okay.
So it's not the same thing. Remember, what we're doing here is we're solving the Schrodinger equation for a particular energy operator, which is p squared over 2m. And when you have a photon, it's different. You have to do something else, bring in electric and magnetic fields or something like that. It's just different. We start from a different place. We might talk about it later, but it's just different.
Okay.
Okay, good question. More questions. So yeah, it's really powerful stuff being able to just exponentiate this operator and then using its eigenvalues to reduce. You immediately went from the Schrodinger equation to we just jumped to the solution using this bras and cats, and everything else was just like trying to understand what this integral does. but it's not really solving anything. It's just this is the solution already. We have it here, right? And then all we did here was just try to understand this solution in blue, like what does this integral actually give us? And again, we did that by saying that this exponential is very wiggly, except for places where, you know, the exponent is slowly varying, which is around some k bar, where this is stationary. And that k bar is going to correspond to basically going to be the peak of this initial envelope in Fourier space. This gives you the initial momentum, and that's where sort of the contribution to the integral is centered around. So that's kind of the intuition of what happens. But you can sort of, it's nice, you can work this out, this stationary approximation, and what it gives you here, the point is that what it gives you is that your solution to the time-dependent wave function is just like the initial wave function, except shifted by dt. Yeah, so that's kind of cool. You know, and then there's, of course, an overall phase that gets picked up, but that's not physical. All right, so in general, all right, so I'm gonna clear this. That's all I'm gonna say about that, I guess, for now. We can talk some more about the Schrodinger equation. And for the most part, you know, so we looked at the free particle, but, you know, in general, you also have a potential, kinetic plus potential. And so generally, this is your energy operator, kinetic plus potential energy. And, you know, you can still solve this thing, except it's harder when this is around. Why? Because now you don't know what to choose for your basis, right? If you use position, then you'll have trouble here. Oh, sorry, if you use momentum, then you have trouble here. If you use position, then you'll have trouble here. These are not compatible observables, the potential and the kinetic energy. They don't have simultaneous eigenkets. You can't use P, right? And you can't use X because, you know, you'll get in trouble. But we can still think about it as a differential equation, right? We know what these operators do on, say, a wave function, psi of x t, and, you know, just translating immediately from here, we already saw what p does, it just takes derivatives. This becomes IH bar, you know, dt acting on the wave function. This part right here is minus h bar squared over 2m. It's from the two derivatives. IH bar minus IH bar acting on the function. So you got two derivatives with respect to x acting on the wave function. This is just a function of an operator, so all it does is multiply it by the same function, but now as a function of the variable x. And this is the Schrodinger equation you're used to seeing. But I prefer to think of it this way, and then this is sort of independent of the representation, right? I can write it out this way, and then I can do all sorts of things. I can think about it this way in position representation. It might be worth it for you to think about what this looks like for psi of tilde pt. What if you use the momentum representation, right? You might wonder what this operator does on this function. That's kind of an interesting exercise. Sometimes I give it as a homework problem, but yeah, that's the Schrodinger equation. And we know that this part is time independent, the Hamiltonian. So it has stationary state type solutions. We know that in general, the time dependent solution is going to be given by, or at least if you find eigenvalues, so if you find eigenstates of H, you find the energy eigenstates, then we know that these guys will just evolve according to a phase, right? It'll be given by E to the minus IT over H bar times the associated energy with that size 0. They'll just evolve with this phase equal to the E to the I T over H bar times the energy eigenvalue. And so a lot of times in undergraduate quantum, and we'll do this too, a lot of times you spend time looking for those eigenstates of the Schrodinger equation. And that amounts to solving this differential equation now in just space, right? And this is the time independent Schrodinger equation. And you know, it's an important one because even if you wanted the full time dependent solution, you know that the best way to start, right, is to find something that gives you a nice basis and, you know, is an eigenstate of your energy operator. That's what you want to do. So this is where you would start, is by finding the eigenstates of your energy operator in this, you know, functional language, which means solving a differential equation. So we'll spend some time doing that for various problems. We'll look at that, like a particle in a well and things like that. We'll look at different, you know, so in undergrad, you spend a lot of time thinking about different shapes for the potential. You know, people do kind of infinite square well, where your potential looks something like this, where it shoots off to infinity and is 0 over some interval. You know, there's also the classic one, which is a quadratic potential, right? And this is the quadratic potential, that's the harmonic oscillator. Well, there's lots of examples that we're going to do, but that's later. I want to mention some more things related to the Schrodinger equation, in particular, the time-dependent one. And one is probability currents. So we saw that the probability density, right, of observing a particle at some position x at time t is given by the psi. This is the probability density. We have to integrate over x to find the particle in a particular interval in x at time t. But you can actually see how this thing evolves in time. You can actually calculate dt rho. It's very similar to how we calculate the time evolution of like the expectation of an operator. This is, you know, dt acting on psi star psi. You can do product rule, right, and apply the Schrodinger equation up here. So what do we get? We can get this acting on that, right? That's like the time derivative acting on the bra. You can work all this out with bras and kets too, but I'm just gonna sort of write it out. H bar over 2mi. So yeah, this product rule over these two guys. So you get everything acting. No, sorry. Should put in one more step here. So we have psi star partial t psi, right, plus psi partial t psi star. And now we can put in the Schrodinger equation. We know what these two things are by just using the Schrodinger equation or taking its star. That gives you this guy. So what we get is from the Schrodinger equation, you get h bar over 2mi psi star, two derivatives with respect to x acting on psi. You get the v of x term, psi star over I h bar. That's just from the first term. Then you also get plus h bar over 2mi. You get now psi, and now two derivatives of x acting on psi star. And then you get a minus v of x over r h bar psi star. The minus signs here just come from the fact that when you take the complex conjugate of both sides, this part with the I partial t, it picks up a minus sign. So it's nice because then that means these potential terms, they cancel. And what you're left with is minus h bar over 2mi psi star, two derivatives acting on psi, minus psi, two derivatives acting on psi star. And these don't necessarily cancel because this is acting on psi star and this is acting on psi. Here, it cancels because it's just the product of psi and psi star, so you can flip them around. So we can actually write this using the product rule again, except now with the x variable. You can write this as minus h bar over 2mi. And we can write it as the derivative with respect to x acting on an entire thing, psi star dx, psi minus psi dx psi star. Why can we do that? We just think about what happens here. This x, this derivative acting on this term gives me a derivative times the derivative. And acting on this one will give me a derivative minus derivative. So that's 0. So the only terms that contribute are where this guy hits this guy again. So you get this term. And when this guy hits this guy, and you get this term again. So the cross terms cancel. So you don't have to worry about those because it's just the product of the two derivatives subtracted from each other. That's 0. So this is okay. And why would we write it that way is because then we can interpret this as minus the derivative, and you can think single derivative is like a gradient of some quantity j. And this is called a probability current. Why is it a current? Because this equation that you get is the continuity equation. It's the one-dimensional analog of the following in 3 space. Right, I can put this thing on the other side. It's the same as this equation here. It's a continuity equation. It says changes in rho are only due to fluxes of this current. And I'll show you this in a moment. But this is just the one-dimensional version of that. And what's J, just to complete this idea here, it's just h bar over 2mi and the stuff in here, which I can also write as the real part of h bar over im of psi star partial x here psi. You can convince yourself of that because the real part is you take this and you add to it its complex conjugate and divide by 2. So that gives me this factor of 2. And the complex conjugate will give me a minus I, so it'll give me a relative sign difference between the two. So this is just another way of writing that current, a more compact way. So that's what you get. And why is it a current? We can look at it in 3 dimensions. If we think about what this means, if you think about a box and you ask like what the probability is inside the box here and how it changes in time, then the change inside that box of, say, the probability inside the box, we're going to integrate over, all the positions inside this box, mass and volume, of the probability density. How that changes in time, if all that's happening to the probability is that there's probability currents in and out of the box, where we can define the surface area of the box as, with a little vector pointing outwards. So then any change in the total probability in there must be coming from any current that is coming either in and out of the box. And we can calculate the current by looking at the surface of the box and calculating the current, dotted into this surface element. And by convention, the surface element is always out of the volume. So if J dot ds is positive, that means the current is pointing out of the volume, right? And so we're losing probability. So the change in probability must be minus the integral over the surface of the box of J dot ds, right? And we can use the divergence theorem. I forget what it is. It's one of those Green's theorem, one of those calc theorems from multidimensional calculus, that the current dotted into the surface element must be equal to the integral over the volume of the box of the divergence of the current. And if we look at this, we see that this should be independent of the particular box that we use. So in order for this equation to hold true for any arbitrary box, then you must have that d rho dt is equal to minus the divergence of J. So what this is saying is that the change in the probability is just due to this probability current that either moves probability in or out of a particular region, in this case an interval on the real line. And that current is just given by the wave function itself, this h bar over im psi star partial x here aside. This tells you kind of the so you could say the velocity or something, the current of the probability in and out of a particular region around x. Let's do an example, see what this kind of J is. It should be a kind of natural thing. It should make some sense. For instance, say we have just like a particle moving with some momentum p. Then we know that the associated wave function is a e to the I p x over h bar, right? It's not normalized or anything, but that's the relevant term. We can use this to calculate J, which is the real part of h bar over im. We have a star e to the minus ipx over h bar. Then you have the derivative with respect to x. That'll pull down the factor of ip over h bar here, and then you have a e to the plus now ipx over h bar. To calculate the real part of that, well, this a multiplies this a, you get magnitude of a squared. And the only parts that the i's cancel, the h's cancel, you get p over m. So you see, it makes sense. It kind of tells you that the current is the magnitude of the wave function at that point, it's the magnitude of the wave function, right? Times the velocity. So it's kind of like the velocity times the kind of amount of probability there. So that kind of, this is the velocity of the particle. So that's that makes some sense. All right, and that's kind of it for the basics of wave mechanics. Next, what we should do is just look at different, examples, well, we studied the free particle. Now we should just look at, more more examples of Hamiltonians that are maybe more complicated with like a particular V. And it's important to remember the probability currents. They tell you about the actual probability of observing a particle somewhere and how that evolves in time. That's what basically the Schrodinger equation in probability takes the form of this, for the probability takes the form of this conservation law. We might come back to this. This is useful in certain situations when you're interpreting. You see, the nice thing about this, I didn't say, is that I can kind of use a stationary solution for psi that doesn't depend on time to calculate this current, because the current only depends on sort of spatial derivatives of the wave function. So that'll come up, because in physics, especially undergraduate, sometimes you end up solving problems like scattering and things like that without doing the full time-dependent solution. You end up just looking at the eigenvalues of this time-independent Schrodinger equation and then interpreting them, those solutions, as sort of scattering states, for instance. So, and of course, we know that more properly speaking, if you're doing something like scattering, you would want to set up a wave packet. And the thing that lets you sort of convert between the two different things, the wave packet stuff we looked at with the time-dependent Schrodinger equation, the time-independent one, it'll be helpful to think about probability currents in that case. So this will be important for scattering, which we'll do a little bit of. But I wanted to at least introduce you to the concept of a probability current. So I guess that brings me to the end of the time. It's a good place to stop. Next time we'll do a time-independent Schrodinger equation. We'll do like a, square well, things like that. We'll do this kind of potential, a barrier. This is all different potentials we can study. And we'll also do the harmonic oscillator, which is the quadratic potential. So that's what we're going to do now, is we're going to look at different potentials, try to understand them. We won't solve the time-dependent problem, but keeping in mind this idea about currents, we will sometimes be able to interpret the stationary, the actual time-independent solution. We'll be able to like fiddle with those in order to understand what happens in the time-dependent case. You can actually make Mathematica solve the time-dependent Schrodinger equation for this potential, and you can like see the particle oscillate, like a little ball on a spring. It's kind of cool. Maybe I'll show you that too. All right, any more questions about that? And what we're doing, what we're about?